Thank you, Chairman Gordon and Assemblyman Santiago, for coming. I have to say, I think the absence of your colleagues may perhaps reflect a hope that the El Nino actually will solve our problems and none of this will be relevant. I think, as some of the earlier speakers have said, even a wet year isn't going to solve our problem. I think, as some of the representatives from the state agencies recently said, we have a lot to do on water. So the name of the panel is Consumption and Alternative Resources, and the section that we're in is supposed to be the strongest options. I have to say that I agree with almost everything that the previous speakers have said. We have a lot of problems with California water, and we have a lot of options. The one area I might subtly disagree with is the all-of-the-above approach. I feel very strongly, as do many of my colleagues in the room, that we have to take a portfolio approach. There are a lot of things that we have to do. There is no single silver bullet solution to our water problems. That's a little different than saying we have to do everything all at once. We can't afford to do everything all at once. Not everything is equally economically appropriate. Not everything is equally regionally appropriate. There are priorities that need to be set. And what I would like to do just briefly is talk a little bit about what I think of as 4 key priorities that make the most sense from an economic perspective, from a resource availability perspective, from a priority perspective. We're in a drought. It's not just California, it's the West as a whole, of course, but California has really borne the brunt of the drought for the last 4 years. As you heard previously, it's not just been dry, it's been extraordinarily hot. And here's California. This is the drought monitor. It's updated every week by the University of Nebraska. It's a great resource. And apparently there's some tiny part of California down here that is not in drought. That happens to be part of the heart of the Mojave Desert, so I'm not sure how relevant that is. But we're in a bad drought. And part of the consequences is this massive overpumping of groundwater that you've heard about. This is a graph that shows from 1962 up until pretty much a year ago. We get a little bit of a rebound during really wet years. Some of our groundwater might recharge again, but there's been this long-term inexorable drop in groundwater. Groundwater is a resource, but we're overtapping it, and that's unsustainable, and we know that that's a problem. I'm going to talk about a report that we issued about a year ago and we've updated called Untapped Potential. It was a project of my institute, the Pacific Institute. We're a nonprofit research institute working on global water issues with some participants from the University of California, San Diego, and from the Natural Resources Defense Council. And the key findings of that are there's been enormous progress over the last several decades in capturing improvements in water use efficiency. That's the consumption part, the demand part of this select committee's purview, and at developing local supplies. And previous speakers have talked a little bit about both of those. We are, however, still living beyond our means. We're taking too much water from our rivers and streams, and especially from our aquifers. Even in a wet year, we overpump our aquifers, and that is unsustainable. And the good news is that there are great opportunities to both reduce consumption, that's the consumption part of this committee's purview, and to expand local supplies, reducing consumption on the urban and agricultural side and expanding supplies through a variety of different pieces. And I'm going to talk in particular about 2 of those, stormwater capture and reuse. Water use in California, I don't really need to go over this. Jay Lund talked about this. Alan Hannock did as well. Most of the water that humans use in California goes to agriculture, 80%. 20% goes to urban use, which is commercial, industrial, residential, institutional. And residential use is largely indoor. It's a mix of indoors and outdoors, but the untapped piece is really largely outdoors. We still use a lot of water outdoors. So we looked at 2 different scenarios for urban conservation improvements. And by urban conservation improvements, we looked at things we can do indoors to do what we're doing more efficiently. Better toilets, better washing machines, better dishwashers, reducing leaks. Things we can do outdoors, the landscape question, which has gotten a lot of attention in the last year or 2 of drought. We're finally beginning to address outdoor landscaping. And we looked at an efficient scenario, and we looked at a really efficient scenario. And the efficient scenario suggests that we could save another 2.9 million acre feet in indoor conservation if we were really aggressive at outdoor landscaping in particular, but also at reducing leaks and swapping out the remaining inefficient appliances. Perhaps we could save as much as 5.2 million acre feet. We started the day with a conversation from one of our colleagues in Israel. And one of his comments was, you asked what should we be doing first and how have you done on conservation? And his comment was, we've really put a lot of time and effort into urban conservation, and urban water use in Israel is far smaller than urban water use in California per person. They've done a lot of the things that we've done, but they've done more of them. That was the first thing they tackled, and it's the first piece of this untapped potential that we addressed in the report. So here's just a quick example, looking at, it sounds mundane, but looking at toilets. In 1980, the state of California used between 700,000 and 800,000 acre feet for toilets. That's how much water we flushed down our toilets in 1980. And that's around the time when the state of California put in place the first toilet efficiency standards. Led the nation in that. Let's see, where are we? Today, if every toilet in the state was that same old 1986 gallon per flush toilet, with population growth, we'd be using 1.2 million acre feet just to flush our toilets. That's how much we would be using if California had not put in place these standards. In fact, current water use for toilets alone is about 550,000 acre feet. It's less than it was in 1980, even with population growth. That's because we've moved on improving the efficiency of toilets. And if every toilet in the state today was the most efficient toilet, a 1.28 gallon per flush toilet, that's the current standard in the state of California, but not all toilets are at that standard, we'd be using a little over 200,000 acre feet for toilets. With a much bigger population, we'd be using a quarter what we were using in 1980. It's a good example of both the progress we've made and the untapped potential, the ability to do even more. And of course, toilets is a piece of the puzzle. There's washing machines, there's dishwashers, there's leaks, there's outdoor landscaping. So yes, we've made great progress. Yes, there's more to be done in indoor and outdoor residential use. On the horizon, there are new appliances, there are new standards. Again, California is leading the nation on appliance efficiency standards, both for water and for energy, I would note. There's remote sensing to help us manage our outdoor water use better and develop water budgets. There's social norm-based efficiency tools. We're beginning to get in our mail information about what our actual water use is from our water utilities and compared to our neighbors. I get a little thing that tells me that I'm using more water than my neighbor, which frankly I find hard to believe looking at my lawn and his. I don't have a lawn, and his lawn. But these social-based tools are beginning to provide information for people to help them improve their efficiency. And advanced meters. We've had some conversation about not everybody has meters, but at the same time, there's some new meters that are offering enormous value for us at improving efficiency. This is just a pie chart for each of the major regions in the state showing the additional potential that we can achieve. Again, the biggest pie charts are in the big urban areas, of course, in the San Francisco Bay Area and the Los Angeles area. It's broken out by residential indoor, which is the dark blue, residential outdoor, which is the light blue, and those are the biggest piece of the puzzles. But there's also enormous potential in some of the big cities in the Central Valley. And there's potential basically everywhere we go. I'll skip this, but this basically shows additional potential in faucets, in showers, in clothes washers, in toilets, leak repair. There's a lot of potential still untapped. So the good news is, as you heard from Deputy Director Bishop from the State Board is keeping track of this to meet the governor's targets, the state targets for conservation. And we've been meeting the 25% statewide conservation targets. Between June and September of this year alone, the conservation and efficiency improvements in the urban sector of California has saved almost 800,000 acre-feet of water. Some of that is permanent improvements because we're changing out our gardens, we're swapping out our toilets and dishwashers and that sort of thing. Some of it is temporary, it's behavioral, and we'll go back when it's a wet year, we slip back a little bit. But not only have we met our targets, or not only have we saved almost 800,000 acre-feet, I would note that that amount of water saved between June and September is far more water than any of the new proposed reservoirs that we could plausibly build would provide in terms of new water. At most, those would provide a few 100,000 acre-feet of water. Conservation and efficiency is what's doing the job for us here, and that's an incredibly important message to get across. Agricultural efficiency, we haven't talked much about ag in this workshop, but there's enormous potential for doing more with the water we spend for agriculture, growing more food with less water through some of the same kinds of changes in technology, like irrigation technology, changes in irrigation practices like when we choose to water and how we deliver water to farmers. And because agriculture uses such a very large fraction of the total water used in California, the potential is much larger. The percentage savings may be lower than in the urban sectors. That may be questionable, but the total volume of water is very significant. And we've seen farmers moving in this direction for decades. They're swapping out irrigation systems, they're changing crop types, they're improving soil moisture monitoring, they're doing some of these things already. But again, enormous untapped potential on conservation and efficiency. I'll skip this. On the supply side, again, we heard some of the previous speakers talk about all of the different options that are available. I'm just going to talk about recycling, wastewater recycling, and stormwater reuse because they have enormous potential. And again, we heard some of this already. We are currently using around 600,000 acre-feet of recycled water statewide. Again, you heard the professor from Israel talk about how they're recycling 85% of their water now. They're using it for agriculture. We're using about 13% of our wastewater statewide now. And we don't use it for agriculture. We're not going to ship it long distances to the Central Valley. But we use it for landscaping. We use it for groundwater recharge. We've heard we use it for power plant cooling. We use it for ecosystem restoration. There are lots of things that we can do with it. And in the report that we put out, we looked at two scenarios. One is to double that to 1.2 million acre-feet, and that's a very easy target. You, in fact, heard Deputy Director Bishop say that the state's target is 1 million acre-feet by 2020. I think we'll meet that, especially with the renewed attention to it. And 1.8 million acre-feet was the high potential, relatively cost-effective. The state's target is actually 2 by 2030. I think we could meet that long before 2030 as well. That's an enormous amount of water. That's water that we already have, that we already capture, that we already treat, and as somebody has noted, we throw away into the ocean. Let's put that to use. Stormwater capture is the final piece of this. I have an op-ed actually in today's LA Times, coincidentally, in terms of timing, about stormwater capture potential and some of the new projects that are underway in terms of stormwater capture, especially if it's going to be a wet year. If El Nino delivers a lot of water, we have to get better at capturing what we get during the wet years. We use it for recharge of our groundwater inland, and we can do that in the coastal areas. There are lots of methods and use strategies for doing that. I won't go into that. Look at the op-ed. It's fairly short, and it describes some of the tools that we can and ought to be using for stormwater capture. But the potential, again, is enormous. 500,000 acre-feet at least of stormwater capture in San Francisco Bay Area and the Los Angeles areas in particular. Although I would note there's enormous potential that we did not look at in the study for stormwater capture in the Central Valley. This is different than urban stormwater capture. It's basically figuring out how to capture more of the stuff that comes down our rivers in the flood times, spread it over some of the ag land, and recharge those groundwater basins that are very badly overdrafted. This is an overview of putting those four pieces together: ag efficiency, urban efficiency, stormwater capture, wastewater. The size of the pie, again, suggests where the biggest potential is. The blue is reuse potential, biggest in the coastal areas. The green is ag efficiency, obviously biggest in the Central Valley where the ag water use is. So we're facing a drought of unprecedented proportions. It's affecting our ecosystems, it's affecting the population, it's affecting our economy. We heard earlier a good summary of that. Even in an average year, we're living beyond our means. We're taking too much water from especially our aquifers, but some could argue, as I think Jay Lund suggested, maybe we're taking too much water from the Delta. And in the long run, maybe we should be looking at taking less from the Delta. We've made considerable progress at improving urban efficiency and ag efficiency and improving local supplies, but there's still enormous untapped potential in all of those areas. And these four things are the cheapest, fastest, most environmentally sound things we want to do. Again, the question came up this morning about desalination. They're building a big desalination plant in San Diego. It should go online, supposed to go online this year. We're still waiting. It's going to be the most expensive source of water anybody has in California. And there's still enormous untapped, cheaper potential in San Diego for other things. Israel is moving to desalination, but they've already restructured agriculture. They've already moved aggressively toward wastewater reuse. They've already cut their urban water use in terms of per capita use substantially below even where we are now. Let's do the things that make sense in the right order, and I think we have enormous potential to solve our problems. Thank you very much.
Great. Thank you, Dr. Glick. And finally, for presentation, Dr. Buzz Thompson. Dr. Thompson is Director of Stanford Law School's Environmental and Natural Resources Program, and also a Senior Fellow at the Woods Institute for the Environment at Stanford.
Okay. Thank you very much, Chairman Gordon and Assemblyman Santiago, for inviting me today. It's a privilege to be here. There are obviously a few questions that are facing the state today that are more important than the questions that you've been addressing in the hearing this afternoon. And I would say the most important of those questions is how do you increase the long-term water security and resilience of the state of California? I think you're going to find at the end of the day that, as Peter has already suggested, there's a great deal of consensus amongst the people who are working in this particular area. And my guess is that there's also not going to be any disagreement between Peter and the rest of us that although there are a lot of potential solutions, one of the things that we need to be doing is thinking about how do you prioritize amongst those, and there are some solutions that are better than others. There are probably two key messages that I have this afternoon. One is that, as I think Peter has just shown, there are already many opportunities for providing greater water security and resilience to the state of California. And one of our problems is we are not taking full advantage of those opportunities at the moment, and we need policies that push us in the direction of ensuring that water suppliers throughout the state take full advantage of them. The second message, though, is that no matter how many opportunities we face today, new technologies will be coming along over the next 5 years, 10 years, 20 years that will provide us with even more opportunities and will reduce the costs, both financial and in terms of security, of the options that we face today. And that, again, we're really not supporting and encouraging the development of new technologies as much as we might. So in terms of policies, they're both important policies to encourage greater adoption of the technologies and options that we already have, as well as policies that will encourage new technologies. So what I want to do is just briefly, sort of quickly rush through a variety of different options, some of which Peter has already covered, and so I will go quickly through those. But when I look at the options that the state of California faces in order to provide greater water security, they are basically conservation. That's the demand side of the equation, as well as storing water when we have water available, and diversifying the stream of water supplies that we have, particularly diversifying into water sources such as reuse that help protect us against droughts because they are not as susceptible to drought shortages. So turning first to conservation, as Peter has already mentioned, conservation provides us with the low-hanging fruit today, just as it does in the energy sector. Peter showed you some charts that he and the Natural Resources Defense Council have put together in terms of options for municipal water conservation. This particular chart comes from the 2013 update of the California Water Plan, and just like Peter's charts, this shows that there are immense options. The only disagreement between the California Water Plan and Peter's study is the total amount of water conservation available. State water plans suggest about 2 million acre feet at the moment. Peter suggests 2.9 million acre feet at the low end, maybe as high as 5.2 million acre feet. I actually think Peter's numbers are probably more reliable than those, or probably more accurate than those in the state water plan. But the bottom line is that we have tremendous opportunity. And there are companies that are developing every day and new technologies that are coming along every day that will permit us to conserve even more water. You earlier today had a speaker from Israel. This is a Israeli company, Takadu, that works with municipalities around the world, taking the data that is available on water supplies, combining it with various statistical algorithms to provide real-time, actionable alerts as to when there are leaks in the water system, when there are likely to be bursts in the water mains, where there are anomalies that can be eliminated and greater conservation actually pulled out of the water system. For Queensland, Australia, they've already saved that utility about 1 billion gallons per year. In Israel, they have gotten Jerusalem down to what's known as non-revenue water, the water that is lost in the system, to less than 10% of the total amount of water that is utilized. So far, they do not have any contracts in the state of California, at least the last time I checked. The second option is storing water. Historically, what we have done is to store water in reservoirs like this picture of Diamond Valley Lake, and that has been immensely important in periods of drought. The problem is that new surface storage is expensive. In addition to that, we are running out of the best reservoir sites for new surface reservoir. And so another option that the state has been using to an increasing degree is to actually store water when it is available in groundwater aquifers, and then after storing that water in the aquifers during the wet periods, then recovering it during the dry periods. Here again, there is immense potential. So if you take the total amount of surface storage available in the state today, it's about 50 million acre feet of storage capacity. If you look at the potential groundwater storage available, it is something in the nature of 17 to 25 times the surface capacity. Again, it is less expensive. It is faster to implement. It is generally less controversial. One of the problems, however, is that we are still working in 20th century science in actually understanding our groundwater aquifers and figuring out how best to store the water. This is a picture of some work that is being done by Rosemary Knight at Stanford, looking at using geophysical techniques, much as you use in the oil industry, to get better senses of our groundwater aquifers. The best way I think about this is it's effectively like using a CAT scan for evaluating and characterizing groundwater aquifers. One of the first things that she worked on is a groundwater aquifer down in the Monterey area, where the water that was being stored, when they went to pump it back out, they found that they were only getting about 70% back out of the amount that they originally had stored. That was because they had a very poor model of that groundwater aquifer. Rosemary was able to go in without drilling any wells whatsoever and actually determine where that water was going. So here's another example of how new technology can help on the options that we already have. The final option is to diversify, and there are a variety of ways in which we can diversify our water supply. One, which again Peter talked about already, is stormwater capture and reuse. use. One of the problems, again, with stormwater capture and reuse is that stormwater frequently is contaminated with a variety of different pollutants. But here again, there's work taking place in the state right now to develop new technologies that hopefully will permit us to capture stormwater and then let that stormwater filter down into groundwater aquifers and produce much cleaner water than we have today. There's a program in California right now called Renew It. It is a joint program between Berkeley, Stanford, also the Colorado School of Mines, and New Mexico State. And they're specifically looking, in this case with the Orange County Water District, at how new infiltration materials can actually, again, produce cleaner water through stormwater capture. Another option is gray water, the possibility of recycling the water on an individual household basis. So gray water is basically everything you see in this particular picture except for the toilet, which is the black water. Gray water is frequently subdivided into what's known as light gray water, which is what you'd find coming out of your shower, your bathroom sink, your washing machine, as well as heavier gray water, which would be what you have out of your dishwasher and your kitchen sink, because generally those are going to be slightly more polluted. The idea, however, is that rather than worrying about this on a centralized basis, can you do this on an individualized household basis so that you're able to basically take the gray water and use that for irrigation? And there was a study done in 2009 by a UCLA professor that in this particular chart shows the opportunities for gaining additional supply from gray water operations and comparing that to the typical individual demand for water on the right-hand side. And you can see here that if you were able to get everybody through gray water systems to recycle their laundry and their shower water, you would basically have enough water to provide all the water that we need for outdoor landscaping. And if you add to that gray water from dishwashers and kitchen sinks, your heavy gray water, you would also provide enough water for about 40% of toilet use. Peter also has already talked about the opportunities for recycled water. As Peter pointed out, we've had tremendous growth in the amount of recycled water in the state of California over the last 30 years. But as Peter has also pointed out, we're only recycling about 13% of all of the wastewater that we're actually producing in the state. Peter also showed a small version of this particular chart, which simply emphasizes that there are a tremendous number of uses of recycled water, so that if we can recycle that water, there's no problem in finding actual uses. One of the problems with recycled water, however, is it is more expensive than a variety of other sources of water because of the immense amount of energy that is used in producing recycled water. In fact, generally, the most consumptive energy use in a municipality is going to be its wastewater system. Here again, their faculty, in this particular case, you see Craig Criddle there in the middle, as well as Tom Cantwell on the far left. He's actually a rocket scientist. Craig is a civil and environmental engineer. They've come up with a new system called CANDO, which maximizes, given current technology, the amount of energy you can get out of your recycling system. This particular chart shows the theoretical amount of energy that you can get out of wastewater treatment. And what you'll see is that the total amount is something in the nature of about 2.6 kilowatt hours per cubic meter of wastewater. And wastewater treatment itself only consumes about 0.6. So in theory, you can actually get more energy out of your recycling of wastewater than you have to put in to actually operate the system because of the energy which is embedded in the wastewater itself, and CANDO is likely to be a net positive energy contribution. One of the problems, again, though, is that a lot of utilities are very conservative. They're reticent, therefore, to test out brand new technologies. One of the things that we are doing at Stanford right now is we are building the Codiga Resource Recovery Center, and we're actually planning, starting next year, to scalp our own sewage water and then utilizing CANDU and various other technologies actually test them out, because we think that's the only way we can actually get them out and utilized in a quick fashion by utilities throughout the state. Another type of reuse that we are not taking full advantage of is reuse of contaminated groundwater. This particular chart shows the results of a study that was conducted by the San Francisco Bay Regional Water Quality Control Board back in 2012. And what they were interested in is we have a lot of contaminated groundwater today. We pump that groundwater up, we treat it, and then frequently we simply dispose of that groundwater rather than reusing it. So if you look at all of the sites in the San Francisco Bay Area where we are currently actually taking contaminated groundwater out of the ground and treating it, how often are we then going on to actually utilize that? Of the 49 sites that they looked at, only 6 of them at that particular point in time were reusing the treated groundwater, and you can see the various sites listed here. How they were utilizing the water. The blue line is how much water they were actually extracting and treating. The red line was how much they were actually then using. And in total, only about 20% of that treated groundwater was actually being utilized. And if you could have utilized all of the rest of the treated groundwater, that would have been about an additional 1.3 billion gallons of water every year. Let me just finish with desalination. I agree entirely with Peter. I think that at the moment, desalination is really only an option for those regions that have really no other way of increasing their water supply. The reason is that no matter how expensive recycled water is, desal is even more expensive because it uses much more energy. And you can see in this particular chart, the line on the left shows the total energy needed in desalination, whereas you can see the next two are wastewater reuse. So we need much more energy in those particular contexts. But again, here is a need for new technologies. This is a chart from the U.S. Bureau of Reclamation in 2012, which you can see the diamonds on the bottom are showing the theoretical minimum amount of energy needed. And then you can see up in the top, those are the various boxes with the arrows pointing to them, the amount of energy used by a variety of current plants in the United States. You'll see, however, that there are some new plants that are coming on that seem to be reducing the total amount of energy needed, the major one being a Siemens plant that was constructed on an experimental basis in Singapore. And there are opportunities down the road for reducing the total amount of energy used, particularly by finding new forms of membranes to actually use in reverse osmosis. One of the options that people are paying a lot of attention to is graphene, which could have the potential of reducing energy use by somewhere between 10 and 40%. This brings me to my final point, which is that at least compared to energy, there is an innovation deficit in the water field. This particular chart shows the number of new patents that have been issued in 1999 through 2011 in the water field, and that's the green line you see at the very bottom. And then in the clean energy area, that's the blue line that you see on top. And you can see that we were always issuing more patents in the energy area than in the water field. You can have a question as to whether or not that was appropriate or whether or not that indicated a deficiency in the amount of new technology we were developing in the water field. But you'll also see starting in about 2005 that the number of new patents in the clean energy area takes off, where the number of new patents in the water field basically flatlines. We did a study last year of innovation in the water field, and no matter how you measure innovation, the innovation in the water sector is a mere fraction of what it is in the energy sector. We also looked at inputs, the amount of money going into the energy sector versus the water sector. And not surprising, you find exactly the same thing there, that no matter how you measure it, there's much more money going into new energy technology than into water technology. And there are a variety of governmental policies that could help promote those new innovative water technologies. This is simply a list, and I won't go through these, but this is simply a list of the policies that we have employed effectively in the energy sector. And the question that I think we should be asking ourselves going forward is, why are we not employing even more of these particular policies in the water sector, and where we are employing them, why are we not employing them to as full of an extent as we are in the energy sector? So thank you very much.